I'm going to solve that one. And so how do I solve it? It's where the blue one hits the red one, right? So it's where the square root of x equals x minus 2. Yeah? Isn't that where it is? How do you solve that equation? Yeah, so this is called a radical equation or a square root equation from college algebra. And the first step to solving one of these is to isolate the square root. Get the square root by itself on one side of the equation, which it is. Then I will square both sides. So if I square the left, if you need to write that down, this is a square root equation or a radical equation. You can go back and review what you need to review. Okay, I square both sides. The left side just becomes x. The right side is x squared minus 4x plus 4, right? Because you have to actually FOIL out the right-hand side, right? Expand it all out. And then solve this quadratic equation, move this over. So you get 0 equals x squared minus 5x now plus 4. And do we have any solutions here? Can you factor that?
Yeah.
What is it?
X minus 4.
X minus 4? Minus 1. Good. You have two answers. What are they? 4 and 1. Right? Those are the two solutions. Does 4 work? 4? What's square root of 4? What's 4 minus 2? 2. So it works, right? Does 1 work? What's square root of 1? What's 1 minus 2? Negative 1. 1's not negative 1, right? So I don't know if you remember this back when you're solving radical equations in college algebra, that anytime you square both sides of an equation, you introduce the possibility of what are called extraneous solutions. So you always have to check your answers. Some of these could not be answers. So in this case, the 1 is an extraneous solution, but 4 is legitimate. It works, right? And so I know that this is 4. Okay, we good? All right, let's see if you can keep up with this. So I'm about to set up the integrals. The first integral is going to go from 0 to 2, and it's going to be, well, I could say f of x and g of x and do all that, right? But at the end of the day, isn't it just the top function minus the bottom one? Okay, so what's the top one for me in that first region? And just to be clear, everyone, what I'm doing is I'm splitting this up. I'm out of colors, but I'm splitting this up into two integrals, right? Right here is where I'm splitting it. So I'm going to do, one of them here. It's going to be my first integral, and then this one's going to be my second integral. So my first integral goes from 0 to 2, and it's the square root of x, right? Minus, what's the bottom function there? 0, right? I don't need this, but I'm going to put it there, okay, just so everyone sees. That's the top minus the bottom, right? The top function minus the bottom function, dx. That should give me the area of the first region. And then plus, now my integral goes from where? 2 to 4. And now I do the same thing, top minus bottom. I didn't give myself enough room there. Careful on this. What's the top one? Still square root of x, right? The blue one. But you're subtracting from that what? This line, right? So it needs to be in parentheses, x minus 2, like that. And then for this, you'd have to distribute the negative through, and then could you find the antiderivative?
Yes.
Right. These antiderivatives should be easy for you now, right? Compared to like what we've done, these are pretty straightforward. Yes, get rid of that, just do that. Think you could take it the rest of the way? Good, all right. Dot, dot, dot. So I'm not going to take these all the way anymore. I mean, really, on the next exam, you will have to take some of them all the way. Like this one, we took it all the way to 9 halves. Maybe the first few will do that. But then when we get into the next section, all the problems are going to be set up the integral, but don't compute it, but set it up. So it's all about setting up, setting up, setting up, setting up, setting up. Make sense?
Yeah.
Okay. I'd rather you set up problems, and we can always have the computer calculate it, right? But if you go and, well, yeah, let's move on. All right, I want us to look at something something different here before we proceed. So how about this? What if I draw this? And then I draw this. And I ask you for the area between those two.
No, it's right minus left.
Well, the first thing you have to notice is that these are not functions of x anymore because they fail the vertical line test, right? They fail the vertical line test. If I were to draw, see, even if you started to think, oh, I'm going to draw a rectangle in here, right? Imagine if you drew this rectangle in here, like that. What's the curve on top? The red, right? And what's the curve on the bottom? The red. So what's the red minus red? Should be 0, right? Doesn't make any sense, right? The only way this would make sense is if the curve on top and the curve on the bottom are different, right? So do y'all see this should not work the same way? There's a problem here. These are not functions of x. However, these are functions of y. And they're functions of y because they pass the horizontal line test. So if you draw a horizontal line, you'll only hit the graphs one time, yes? So what I'm going to do is I'm going to call this red one, blue one, call that blue one f of y. See, it's not a function of x anymore, it's a function of y. And I'm going to call the red one g of y. Then, where they hit each other, like this, I'm going to project out to the y-axis instead of down to the x-axis. I'm going to call this C and D, just so we don't confuse it with A and B. And then when I draw my rectangles, instead of drawing vertical rectangles, I'm going to draw horizontal rectangles. So my rectangles will go like this. And so the total area of this is what happens when I add up all those rectangles. And I want these rectangles to start down here and move up like this, right? So the distance from here, sorry, let me do it this way, that was weird. Okay, there we go. The distance from there to there should be what? Y, not x, right? X was this left and right motion of the rectangle. I want my rectangle to go up and down, so I want to vary the value of y. So this integral, see, I want you to look at the integral as a tool. It's a tool for adding things up, all right? That's what it's for. What you add up is kind of up to you, all right? So I'm going to add up things, and what do y'all want? Do y'all want to do the limits first, or do you want to get the formula? Limits, formulas? What makes more sense to y'all? Let's do the formula first, because I think the formula will help me make another point. So what is the area of that rectangle? Think about that rectangle. So if I draw it over here, right, I have my, let me do it this way. Get rid of this. If I draw just that rectangle, here's my y-axis, right? Here's my x-axis. Here's my rectangle. The blue curve is on this side. The red curve is on this side, right? How thick is the rectangle this way? dy. That's dy now, right? Not dx. It's not the width of the rectangle when it was vertical. It's the width of the rectangle this way. So I should have a dy here, right? So that's this distance right here, dy, not dx. This distance will be, well, we know the distance from here to here is f of y, right? That was f of y. That's this blue curve. And then the distance on the inside here from here to here should be g of y. So the distance we're interested in from here to here should be the f of y minus the g of y. Right? That's that distance. So that's what should go here, right? F of y minus g of y dy. And now my limits go from where to where?
Right minus right to left.
Okay, which for us in this picture is from C to D, right? But those are y values, aren't they? These are y values, not x values. That's why I wanted to do this first. This hopefully shows you that everything you should have in this expression should be y's, not x's. And so your limits of integration should be y values, not x values. Okay? So, with that said, I want us to revisit this problem. I want us to revisit this. I'm going to go back to this and look at it again. I'm going to draw the region again, just so we can kind of analyze it. It looked like this. We had the blue one was the square root that looked like this, right? We had the red one, which was like this. Oh, no, it wasn't. That totally screwed that up, didn't I? I forgot. It was moved over, right? Yeah, so, okay. So the blue one was like this. And then the red one was down to, so here, and then it went up like this, right? And then we had the green one that was y equals 0 here, like that. That's what we had, right?
Yeah.
And what we did correctly. We decided to use vertical rectangles, right? But we had to switch our formula somewhere in the middle because the rectangles, the top and bottom switched, right? So we took care of it. Here it is, all right? What if instead you looked at it from this perspective? What the hell?
You might be there for another 5, 10, or 15 years.
I don't understand. My phone's not supposed to just like let me do that in my pocket. Hold on. There we go. Turn it outwards instead. All right. So instead of using vertical rectangles, what if I drew horizontal rectangles? So if I did that, do you all see that no matter where that is in this region, the function that's on the right is always the red and the one that's on the left is always the blue, no matter where you draw it, right? We never would have a switch, right? We would never have to switch like we did in this one, right? We would just have a single integral. But instead of going from, like here it was 0 to 2, then 2 to 4, we're going to have to figure out here to here, right, where they hit each other. We would need to know what this is, right? And then we'd need to know, well, this I hope is obvious that that's 0, yeah? So doesn't it seem like it would be more efficient to look at it this way? The big difference, though, is that we can't use these as functions of x. They have to be functions of y. So earlier we said a function of x is something where you've solved for y, right? That's what a function of x is. So a function of y is where you solve for x. So what we're going to do is we're going to take these curves. Now we only really need to look at the red one and the blue one because that's going to, on my rectangle, that's the right and the left, right? So why don't we take both of those curves and why don't we solve both of these for x? We'll do that over here. So I have y equals square root of x. That's one curve. The other curve was y equals x minus 2. Let's start with this one. This one's the easy one, right? Solve for x, add 2 to both sides. X is y plus 2. And so what I can do is I can let this one, this one's the line, right? This is the red one. Should have done it in red. This is my curve that's on this side, right? which in this picture I called the f function, right? I should have done it in blue. Right, that's the curve on the right side of the rectangle. So this one is my f of y. I got my color scheme off. Do y'all see this? My color scheme is backwards, but you know what? I won't even use colors. I'm just going to write what it is. This is f of y equals y plus 2. There we go. And then how do you solve this for x? Yes?
You translate the square root into a squared function on the y. So y squared is equal to x, but then you put a limit where x is, or I'm sorry, y is only greater than or equal to 0.
Yeah, so this right here, you square both sides first, right? And then you get this. But this is that right there, that pictures the full parabola. That's everything. That would come this way also, like that, right? Yeah. I don't actually need to put a limit on it, only because I know I'm going to go from 0 to here, right? So I don't necessarily care about what's going on down here. So this will be my g of y. G of y will be y squared. So you solve for x, you replace x with the f of y notation. Here you solve for x, you replace the x with the g of y notation. How about this top limit of integration? Do we know what that is? Wouldn't you have to set these two equal to one another again? You set that equal to that. That's a quadratic, right? And you would solve it. So I'm not going to go through the work. I'm just going to state this. This intersection right here, you get by setting y squared equal to y plus 2. If you solve that, you should get this to be, what is it, 2, I believe? It is 2. Y is 2. You can just look and see it's true, right? 2 squared is 2 plus 2. We're good?
Yeah, I was confusing myself.
Okay. So here I go. I'm going to set up the integral now. The integral should go from 0 to 2, right? 0 to 2. And then it's going to be the function on the right minus the function on the left. You know, instead of top minus bottom, this would be the right one minus the left one. So the right one is the line, right? So what should I put there? It's the right one minus the left one. What's here? Y plus 2. Here? Y squared. Here? dy. There you go. That's the setup. If you do both of those integrals, you should get the same answer. Which one seems easier, though? Probably the one with y's, right? Because it's easier to find the antiderivative of these. This one has a square root, so you're going to have some weird rational fractional exponents and stuff. So it'll be a little bit more complicated. On an exam, I don't care which way you do it, all right? You're free to go either way on it, but you have to make that decision. If you do it the first way with vertical rectangles, then you're gonna have two separate integrals. If you do horizontal, you're only gonna have one. Questions? No? So I'm gonna just go back to the notes here, and we're just gonna look at these real quick. Woo, dark. Now these notes will make a little more sense. So when I say here, a formula, right? If we have vertical rectangles, in other words, we are working with functions of x. Our rectangles are going to be like this. We've got some top function, some bottom function. We can look at each of the rectangles, break them down, figure out the heights. But at the end of the day, here's the formula, right? We go from A to B. It's left endpoint to right endpoint. It's the top function minus the bottom, right? dx. Now, if we want to use horizontal rectangles, then we're working with functions of y, not functions of x. So we're going to need to go from C to D, right? We'll have some function on the right, f of y, some function on the left, g of y, and then here's our formula. Integral from c to d. The way I want you to look at this is the right function minus the left. The right minus the left, and then dy. That all kind of make more sense now that we've gone through it up here? Any questions? Yes?
So you said right.
Right minus
So,
left.
Similar to like the left has to be greater than the right.
The,
How we did it for the
yeah,
article
you would have to say that, if you're going to do it with this formula, you would have to say that f of y is greater than or equal to g of y. And that would put the f function to the right of the g function. When we're doing vertical rectangles, then we want to say f of x is greater than g of x because that'll put the f function on top of the g function. Yeah? Everyone's good? All right, let's see if we can get a more complicated problem. Here we go. Not going to show, whoa! Not going to show you the picture. I know this weather makes, none of us want to get out of bed this morning. Yes?
If we were to do, like, since there's subtraction between the two functions, we do the integral of f of x or f of y minus g of x or g of y, of those two separate integrals?
You could, yeah, do them separately. You could, yes. Yep.
I just want to make sure that.
Yep. But for most of what we do, it just makes sense to keep them all in one because you can do them term by term when you're doing the antiderivatives. All right. Sketch the region bounded by y equals sine x, y equals x equals pi over 2, x equals pi. Okay, y equals sine x, y equals x equals pi over 2, x equals pi. Everyone should be familiar with the sine curve. Everyone should be familiar with y equals x, the identity function. X equals a constant is what? Vertical line. X equals pi, vertical line, right? So these are two vertical lines. This is a diagonal line, and this is the sine curve. I need to draw them all. Here we go. I'll start with the sine curve. And I'm already, when I'm doing these problems, I realize my first sketch may suck. I might have to draw another sketch, okay? So I'm just going to try and first see if I can get this region without using a calculator or anything else. So let me try this first. So I know the sine function is bounded between -1 and 1, right?
Yes.
I know it goes through one period of sine, right, is in 2 pi, right? And halfway is pi. Okay. Then I have the next curve, y equals x. Y equals x is the diagonal. Where is it? Like, is it like this? Does it cut through like somewhere like that? Or does it go like this? I don't know. My drawing is, I'm limited here, right? I'm a human. I'm not quite sure where this y equals x is. I don't know. Does it even matter? So what's one way I could figure that out? Plug in some numbers? Yeah, let me try. Let me just try. How about this? I know that the peak of this is where? Halfway, right? Between, that's pi over 2, isn't it? Right there? Pi over 2?
Yeah.
We know when you plug pi over 2 into sine, you're at 1, right? But what about when you plug pi over 2 into this? Where are you? Pi over 2. What's pi divided by 2? Is it bigger than 1 or smaller than 1? It's bigger than 1, right? Should be bigger than 1. Pi is about 3 something. Divide that by 2, it should be bigger than 1. So that means that my line here, this line, when you plug in pi over 2, I should be above it, right? So something like this. That's supposed to be a straight line. Okay. The main thing is I know that this point's above, yes?
Yes.
And then I have the vertical line x equals pi over 2, which is this line right here. And x equals pi, which is, let me do the green one. And my picture sucks, okay. That's right here. I'm gonna need to extend my line out more this way. Do y'all see the region bounded by all of those curves? Yeah, do you? I'm gonna highlight it here. It's that region right there. Do y'all see it? Now I'm gonna use the computer to show you the graph just to make you feel better about that. That was just my hand sketch. Here's the actual graph right there. A little better than mine. Questions? Are you going to want to use vertical or horizontal rectangles here? Doesn't matter, okay. If it doesn't matter, what makes more sense? Imagine you have a vertical one's moving from left to right here. You always have the same function on top and the same on the bottom, right? So I move from left to right, this line is always on top and the sine curve is always on the bottom. What if you go this way? It changes, right? It changes. And not only does it change, if you had to solve this for x, it would be easy, right? It's already solved for x, but what if you had to solve this for x? You would have to bring an inverse sine function to both sides. So now you're going to be messing with arc sine. I think it makes most sense to do vertical rectangles, right? So I'm going to do vertical rectangles. Since I know I'm doing vertical rectangles, I know my integral is going to be with respect to x, right? dx. Automatic. Do you know your limits of integration, where you start and stop? Well, that's kind of given to us, right? From here to here. We don't need to find intersections at all. So we start at pi over 2, we end at pi. What's your top curve, your top function? X, and then you're going to subtract the bottom function, sine x. So there's just x minus sine x. There it is. That's the setup of the integral. Could you find the antiderivative of that? Yeah. 1/2 x squared plus cosine x. Evaluated from pi, right? Okay, so you got it from there. Dot, dot, dot. Is it supposed to rain all day, or what? It is, pretty much? Yeah, I had a sweater on this morning, and I walked outside. I said, what the hell? I took my sweater off. I'm like, it's not cold. 60-something, but it doesn't feel that cold. All right. Look at this one. X equals y to the fourth. Do y'all see that the problem right now, the way it's being given to us, it's solved for x? That's already making me think I might be going with horizontal rectangles here. The next one is x equals the square root of 2 minus y, and then y is greater than or equal to 0. Shoot, man, how do we graph this? How in the world do you graph that? You know, I mean, you got to kind of know a little bit about what this stuff looks like. Like if this was y equals x to the fourth, do you know what that would look like? Right? It's almost like a parabola, but different. Yes?
Couldn't you, in theory, put the coordinate system, or the xy coordinate system, but just rotate it 90 degrees? And
You
then you can make the baseline being y, so you can just pretty much do the same thing if it were an x curve, but without having to do all the extra stuff.
Very good observation. That we could just basically switch x and y here, right? Like instead of saying x equals y to the fourth, I could write y equals x to the fourth. I could write y equals square root 2 minus x, and then make this x is greater than or equal to 0. And then that's basically just like turning everything sideways. And then you can do everything with x, right? And when I was a calculus student myself, I thought that same thing. I'm like, why do this? Here's the problem. In Cal 3, you're in three-dimensional space. And you can't do that in three-dimensional space because you have the right-hand rule. So you can't just like arbitrarily change your axes. And so it catches up with you if you get into that habit now. So we're going to be forced to just, well, I'm going to force you to stay here, all right, and try and graph this as functions of y, not functions of x, all right? So do you all have your calculators? We're going to take a pause here. Time out, time out, time out. All right, everyone has a graphing calculator, right, because you're allowed to rent one? All right, so what I'd like to make sure everyone knows how to do, so we're pausing, right? That's my pause button. We're coming back to this. I'd like to see if everyone can graph y equals x squared. And then also I want you to graph y equals sine x. You all know how to do it on your calculators? Who needs help? There's a y equals button, top left corner. Got it? Yes? Okay, and then you should be able to type. You should probably clear out whatever's in there.
Yeah.
Yeah. You should get two graphs. Something, right? Like that? Are y'all having trouble or are y'all getting it? You get it? Who needs help? You know?
Like I plugged it in, but then for some reason when I press graph, it just goes to invalid dimension.
Yeah, so you might have to reset your memory.
That's what happened to me in
Yeah.
the exam.
You know how to reset memory?
No, I do not.
I think the memory, let me see. Oh, my glasses on. Does it say mem down there?
Yep.
Okay, you'll have to quit out of that first.
Yeah.
I would reset number 7. You don't have anything saved on there, right?
No.
Okay, so reset and then do it again. Sometimes what happens is it assigns an actual value to x, and then when you try and graph it as a function of x, it doesn't know what to do. But graph. Okay, we got it? Yes or no? Yes? Okay, can I proceed? Yes? Well, I'm getting to that. I'm getting to this, all right? I'm working up to this. We all need to make sure we can graph a function of x. Yes? Okay, check this out. I want y'all to agree with me or disagree with me. If I pick a point on this curve, the x-coordinate is x, and the y-coordinate is x squared. Y'all agree? Any point on that curve, the x-coordinate is x, the y-coordinate is x squared. On this curve, the x-coordinate is x and the y-coordinate is sine x. Right? Yeah? This shouldn't, I'm not trying to trick you. I mean, this makes sense? You plug in x, x squared comes out. You plug in x, sine x comes out. Yeah?